On Friday afternoon, a wildfire burned straight through the ground beneath NASA's most important listening post. 90 people evacuated a hillside complex in Spain that hears humanity's most distant spacecraft. The fire did not stop at the perimeter fence, and it did not slow down. That complex is one of only 3 places on Earth able to reach deep space. One of the other 2 has been missing its largest antenna since last September, so for several hours on Friday, our link to everything beyond the moon thinned. The dishes are still standing, and 90 people walked away, and that is real. But the question I cannot put down is whether Friday was a near miss, or whether Friday was a rehearsal for something this network cannot survive twice. Subscribe so you see how that turns out, and tell me where you are watching from. Now let us get into what actually happened on that hill. Part 1. The afternoon the fence stopped mattering. Robledo de Chavela sits in the foothills of the Sierra de Guadarrama, west of Madrid. The complex stands outside the town, inside a shallow bowl of dry hills. Those hills were the reason engineers chose this specific ground in 1964. Rising terrain blocks stray radio noise from the city and keeps the site quiet. A quiet site can hear signals that a noisy site would lose completely. But the same bowl that blocks radio also funnels wind and channels fire. That is not a flaw anyone can engineer away after the fact. It is a permanent property of the landscape those antennas were built into. Now consider what this particular July had done to the vegetation around them. Western Europe had just recorded its warmest June in the modern instrumental record. The Copernicus Climate Change Service put the regional average at 20.74 degrees Celsius. That figure sat 3.05 degrees above the recent 30-year baseline. It also broke the previous record, which had been set only 12 months earlier. 2 consecutive record Junes, measured and published in the same corner of the continent. Spain had absorbed 3 separate heat waves between late May and the first week of July. Heat does something specific and irreversible to living plants across a long summer. Green vegetation resists ignition because the water inside its tissue must boil away first. Strip that water out across 8 weeks, and the same shrub behaves like kindling. Fire scientists measure this as live fuel moisture content, and it had fallen very low. Below a certain threshold, fire behaviour stops being predictable in any useful way. Wind and terrain take over, and suppression tactics that normally work simply stop working. So the fuel was ready across central Spain, and then it went up. Spain's Interior Ministry reported close to 10,000 hectares burned in the Madrid region. In neighbouring Villa province the figure ran between 13 and 15,000 hectares. 10,000 hectares is 100 square kilometres of burning ground at once. Picture a square block of fire, roughly 10 kilometres along every single side. Around 70,000 people were evacuated inside Spain across those few days. Across Spain and France together, displacement ran past 267,000 people. I want to be careful here, because those totals moved hour by hour. Evacuation orders kept expanding, so any single number is a snapshot rather than a final tally. The human cost was not abstract, and it was not confined to one country. One person died in Valencia as the same heat system pushed fire across the region. A firefighter died in Caltanissetta, in Sicily, during that same continental heat event. French Interior Minister Laurent Nunez said fires there burned close to 98,000 hectares. Nunez called that figure a historic record for his country. Spain declared a national emergency covering the Madrid region and its surrounding provinces. Prime Minister Pedro Sánchez said the immediate priority was simply to save lives. Spain's military emergency unit took command under Lieutenant General Francisco Javier Marcos Izquierdo. His stated objective tells you how bad conditions had become on the ground. He was trying to stop the Madrid fire and the Villa fire from merging. The gap he defended was a strip roughly 14 kilometres wide near San Martin de Valdeiglesias. Stop and think about what that tactical goal actually means in practice. The concern was not containment of one fire front on open ground. The concern was preventing two separate fronts from joining into something nobody could stop. Spain committed 2,737 personnel to the effort. 426 ground vehicles and 21 aircraft went with them. Crews arrived from Greece, from Italy, and from Portugal to reinforce the Spanish brigades. That is a continental response, rather than a regional one, and it still was not enough. Hold on to the next sentence, because officials do not say this kind of thing lightly. Carlos Navío runs emergency management for the Madrid regional government. Navío said publicly that the fire near the capital was at its peak. He added that it was currently beyond the capacity of firefighters to contain. That phrasing is not a warning issued for dramatic effect on camera. It is an admission that suppression had stopped working on that particular front. When a fire exceeds containment capacity, crews shift to protecting life and evacuating ahead of it. At that point, the fire decides where it goes, and nobody else does. And on that afternoon, the fire went toward Robledo de Chavela. Spanish authorities ordered the evacuation of the entire town without waiting any longer. At the complex itself, staff left the site in several separate stages. Spanish public television confirmed that 90 workers were evacuated from those grounds. The correspondent Lola Cadierno reported that total while the operation was still running. Francisco Martin, the government delegate in Madrid, described the situation there as critical. Hold on to that word, because a senior official applied it in real time. Local officials told Spanish media that the impossible was being done to protect it. It is worth pausing on what those 90 people were actually doing. This is not a facility that runs itself with the lights off. Deep space tracking requires operators present through every shift, around the clock. Spacecraft passes are scheduled to the minute and cannot simply be skipped. Somebody watches each link, monitors signal quality, and responds when something drifts. So an evacuation at a site like this is not simply leaving a building. Equipment has to be brought to a safe configuration before anyone walks away. Antennas need to be parked in positions that protect them from wind. Systems have to be handed off or shut down in the correct order. And all of that happens while a fire front is closing on the perimeter. The staged departure reported by Spanish television reflects exactly that reality. People left in groups as their responsibilities were closed out. The last of them left with fire already visible from the site. Here is what separates this event from every other close call in 60 years. The fire did not stop at the boundary and threaten the site from outside. NASA confirmed that the wildfire passed through the Madrid complex itself, not near it, and not alongside it, but across the ground where 6 antennas stand. Cleared ground, defensible space, and every standard mitigation failed to hold that front. By Friday morning, NASA had moved the site's entire workload to California. The Space Communications and Navigation Program said support transitioned seamlessly to Goldstone. That single word, seamlessly, is carrying an enormous amount of weight. And to understand why, you need to know what those 90 people left standing, because the phrase NASA facility does not begin to describe that hillside. Part 2. What 90 people left standing on that hill? The Madrid Deep Space Communications Complex was established in 1964. Its first antenna, a 26-metre dish, went operational the following year. It is not a NASA-run site in the way most people assume it is. Spain's National Institute of Aerospace Technology operates the complex on NASA's behalf. Under the bilateral arrangement, Spain provides the land and the United States funds the equipment. The people who evacuated on Friday were mostly Spanish engineers and technicians. The complex quietly passed its 60th anniversary in October of 2024. That operating arrangement is worth understanding properly before we continue. The complex is not a piece of American territory inside Spain. It is a Spanish facility hosting American equipment under a formal agreement. Spanish personnel run the antennas and maintain the systems day to day. NASA sets the mission requirements and funds all the infrastructure. The same pattern holds at Canberra, where an Australian agency operates the complex. Only Goldstone sits on land that NASA itself controls directly, which means 2/3 of humanity's deep space capability depends on partner nations. Those partnerships have held for 6 decades without serious interruption. That is not a small achievement in sustained international cooperation. It also means a fire in Spain is a Spanish emergency first. The people making decisions on Friday answered to Spanish authorities. NASA could monitor and coordinate, but it could not direct the response. Its lineage reaches back further than the current site does. Before Robledo de Chavela became primary, there was a station at Fresno Diaz de la Oliva. On the 20th of July, 1969, that Spanish station was listening. It was among the ground stations receiving signals from the Apollo 11 lunar module. When Neil Armstrong stepped onto the surface, part of that confirmation crossed central Spain. That is the lineage of the ground a fire front crossed on Friday afternoon. The site itself is larger than most people picture from photographs. The antennas are spread across the terrain rather than clustered together. That deliberate spacing exists for several very good technical reasons. Large dishes placed too close interfere with one another electrically. They also block each other's view of the horizon at low angles, but that spacing has a consequence nobody ever designed for. It means a fire crossing the site does not encounter one target. It encounters 6 separate structures spread across a substantial area. Each one has its own power feed and its own supporting equipment. Each one has its own cable runs entering from the surrounding ground. Defending a single building from fire is a solvable problem. Defending 6 dispersed structures and everything connecting them is considerably harder. Today the complex holds 6 operational antennas, and the exact inventory matters enormously. Deep Space Station 63 is the 70-meter dish, and it dominates the site. It became operational as a 64-meter antenna in 1973. Some sources record 1974 instead, a small discrepancy I cannot fully resolve. In 1987 it was rebuilt from 64 meters to 70 meters. The reason for that rebuild is a story worth telling on its own. Voyager 2 was approaching Neptune after 12 years of travel through the solar system. At Neptune's distance, the existing dish could not collect enough signal for usable images, so 3 antennas around the world were physically enlarged at very considerable cost. Engineers cut apart working structures because a spacecraft launched a decade earlier needed them. That is the kind of commitment this network was built on originally. Let me say that again, because it sounds like exaggeration and is not. 3 working antennas on 3 continents were rebuilt for one spacecraft. Deep Space Station 63 supports S-band and X-band across its operations. Its receivers extend into L-band and K-band for specialized work. Roughly 5% of its available time goes to radio astronomy rather than spacecraft. Then, there are the 34 meta-antennas surrounding it on the same site. Deep Space Station 65 uses a high-efficiency design from an earlier generation. Deep Space Station 54 and 55 are beam waveguide antennas. Deep Space Station 56 entered service in January of 2021. That antenna holds a distinction worth understanding before we go further. It was the first antenna in the entire network to span 3 frequency bands. S-band, X-band and K-band were all available from its opening. From its opening day, it could talk to any mission in the network's inventory. Deep Space Station 53 came online in February of 2022. Its arrival made Madrid the first of the 3 complexes to finish modernization. 2 antennas at the site no longer operate at all. Deep Space Station 61, which supported Mariner 4 to Mars, was retired. It now serves an educational radio astronomy program rather than deep space work. Deep Space Station 66, a 26-meter dish, ceased operations in 2008. That leaves 6 working dishes, and 6 turns out to be the critical number. 6 is more than either of the other 2 complexes currently has available. Goldstone operates 4 antennas, and Canberra also operates 4 antennas. Madrid operates 6, which makes it the largest node in the network. Let that asymmetry settle, because everything that follows depends on it. On the 20th of April, 2024, something happened there for the first time. All 6 of those antennas pointed at a single target simultaneously. Their outputs were combined into one enormous synthetic receiving system. The target was Voyager 1, and the configuration had never been attempted at that site. The photograph of that moment was taken by Francisco Moreno. It was credited to the complex and to Spain's National Institute of Aerospace Technology. Why anyone would need 6 separate dishes to hear one spacecraft is coming shortly? The answer involves a quantity so small that I checked it 3 times. Before that, one more thing establishes a precedent almost every report missed on Friday. This was not the first time weather has degraded operations at this exact site. In August of 2011, lightning struck the Madrid complex directly. The equipment damage was modest, at roughly $58,000 in value. The operational damage was not modest in any sense at all. That strike caused a loss of command capability and telemetry for multiple active missions. Dawn was affected while it was orbiting the asteroid Vesta at the time. 2 other missions, Themis B and Geotail, lost contact in the same event. The incident prompted lightning protection upgrades across the entire network afterward, so the record already shows weather at this site cutting contact with live spacecraft. 15 years ago that cost $58,000 and some anxious hours. On Friday it was a firefront and emergency chief called Uncontainable, and the site NASA moved everything to was already carrying an injury of its own. Part 3. The antenna that broke before this fire ever started. 8,000 kilometers west of Spain, in the Mojave Desert, stands another dish. Its formal designation is Deep Space Station 14, and its nickname is older. People who work around it call it the Mars Antenna. It earned that name tracking Mariner 4 toward Mars in the 1960s. I need you to feel the physical scale of this thing first. The reflector measures 70 meters across from rim to rim. That surface is wide enough to hold a regulation football field with room to spare. The whole structure weighs roughly 2.7 million kilograms of steel and aluminium. In American units, that comes to about 2,970 tons. All of that mass has to rotate smoothly on command. It must also point with an accuracy measured in thousandths of a single degree. There are only 3 antennas of that class anywhere on this planet. One sits at Goldstone in California, one at Madrid, one at Canberra. That is the complete global inventory of 70-meter deep space dishes. The history of that particular dish explains why it carries the name. It was completed in the mid-1960s for the Mariner program. Mariner 4 flew past Mars and returned the first close images of another planet. Those images arrived on Earth as a stream of numbers. Engineers coloured the first one in by hand with pastels while waiting. The antenna that pulled that signal down is the ancestor of this one. It was originally built as a 64-meter dish, like its Spanish counterpart. It was enlarged to 70 meters in the same program that upgraded Madrid. That enlargement happened because Voyager 2 was heading toward Neptune. 3 antennas on 3 continents grew because one spacecraft needed them. There is a reason so few antennas of this class were ever built. A 70-meter parabolic dish is close to the practical limit for a steerable structure. Gravity itself becomes the enemy as the reflector grows larger. The dish must hold its shape while pointing straight up and near the horizon. Between those two positions, the whole structure deforms under its own weight. Engineers solve that with a design principle called homologous deformation. The structure is built so that as it flexes into another parabola. The shape changes, but it remains a usable focusing surface throughout. The receiver position is then adjusted to match the new focal point. That principle is why 70 meters is possible at all. It is also why building much larger is not straightforward. Beyond that size, the engineering costs rise faster than the benefits do. So this is not a generic piece of infrastructure sitting in a desert. It is a specific machine with a specific lineage in exploration, and it has been unavailable to that work for months. Deep Space Station 14 has been out of service since mid-September of 2025. I want to walk through how it broke, because the mechanism matters enormously. It is the most quietly disturbing detail in this entire story. Understand what this antenna does on an ordinary working day. It is the heaviest hitter anywhere in the Western Hemisphere. When a spacecraft is too far away for the smaller dishes, it takes over. When a mission is in trouble, this is the antenna they book. When a probe is executing something irreversible, this dish watches it happen. It also does something the other 70-meter antennas do not. It carries the most powerful planetary radar transmitter on Earth. That capability comes back later, and it changes this entire story. A dish of this size moves on two axes, like most large antennas. It rotates horizontally on what engineers call the azimuth axis. It tilts vertically on what they call the elevation axis. Between those two motions, it can reach almost any point in the sky, but there is a hard limit built into every steerable antenna. Cables, hoses, and waveguide run from the fixed base into the moving structure. Those connections cannot wrap around indefinitely as the antenna turns. So every large dish has a defined range of safe rotation. Beyond that range, something has to stretch, bind, or tear. Software watches that limit continuously during every single tracking pass. Mechanical and hydraulic systems back the software up as a second layer. The whole arrangement exists, so this exact failure cannot happen. That day, the antenna was tracking Juno, the spacecraft orbiting Jupiter. Juno flies a long elliptical orbit and returns data in concentrated bursts. Tracking it is routine work for an antenna of this class. During that track, the antenna over-rotated past its safe limit of travel. A structure weighing 2.7 million kilograms moved somewhere it was never meant to go. Juno itself is worth a sentence here, because the timing is grimly appropriate. That spacecraft has been orbiting Jupiter since 2016. It flies through one of the harshest radiation environments in the solar system. Its orbit was designed specifically to minimize time spent in that radiation. Every close pass returns data that the mission cannot repeat. So the antenna was doing exactly the work it exists to do. It was pulling down irreplaceable science from a spacecraft under stress. And in the middle of that routine task, it destroyed itself. The immediate result was strain on cabling and on structural supports throughout the mount. But the serious damage came from something nobody would predict. The over-rotation ruptured the fire suppression water lines running through the antenna. Read that again slowly, because the irony is not decorative. The system installed to protect this antenna from fire is the system that flooded it. More than 750,000 litres of water poured into the base. In American measure, that is roughly 200,000 gallons of fluid. And it was not clean water arriving in a controlled way. The water carried glycol contamination from the antenna's own cooling systems. That mixture went into the pedestal and into the lower structure of the mount. It reached spaces holding electrical and mechanical equipment never designed to be submerged. Cable runs sat in that fluid, and so did the control hardware. Everything that makes a Dishon instrument rather than a sculpture sat in it. I want you to hold that image, because we come back to it later. A 70-metre antenna, one of 3 on Earth, drowning in its own firewater. NASA did what NASA does after an event like that. The agency convened a formal mishap investigation board to determine what had happened. That board worked for months and produced a detailed technical report, and what the board found goes far beyond one antenna on one afternoon. Part 4. Why the system built to stop fire is what drowned it. The Mishap Investigation Board dated its final report the 30th of March, 2026. NASA released the findings publicly in June of that year. The agency classified the event as Type A, its most serious damage category. That classification rested on a damage estimate between $4.1 and $4.6 million. Now, $4 million is not a large figure by spaceflight standards. Europa Clipper cost more than $5 billion to build and launch. So if you only read the dollar amount, this looks like a maintenance incident. Look instead at what the board actually determined about causes. The report identified weaknesses in the control software governing the antenna. It identified human error committed during the tracking operation itself. It identified procedures that were inadequate for the task being performed. And it identified an undetected failure in a hydraulic limit system. That last item deserves a longer moment of your attention. A hydraulic limit system exists for exactly one purpose on a structure like this. It stops the antenna from rotating past the point where damage begins. It is the safeguard against the specific failure that occurred that day. According to the investigation, that safeguard had reportedly not been tested since 2004. 21 years passed with that protective system sitting quietly in place. Everyone assumed it worked, and nobody ever verified it against real failure. When the moment came that it was needed, it was not there. Then the board wrote something agencies almost never commit to paper. It found a workplace culture that pressured operators to work as expeditiously as possible. Joel Montalbano is NASA's acting associate administrator for space operations. Responding to the report, Montalbano said the investigation at Goldstone made something clear. He said it made clear that the agency must strengthen its processes. Sit with that finding, because it is the thread connecting September to July. A network carrying more requests than it has hours produces schedule pressure. Schedule pressure then produces operators working as expeditiously as they possibly can. Those operators work on equipment whose safeguards have not been checked in decades, and eventually a 70-meter antenna rotates past its stops and drowns itself. The repair list tells you how serious the physical damage turned out to be. Crews must replace all 11 fluid hoses in the affected systems. They must replace at least 85 of the 114 data and power cables. They must replace all 56 of the structural connecting rods. And portions of the flooded base contain asbestos requiring abatement before other work proceeds. It is worth understanding what a Type A classification actually signifies. NASA sorts mishaps into categories based on damage and consequence. Type A is the most serious category the agency applies to equipment. It triggers a formal independent investigation board rather than an internal review. That board has authority to examine procedures, culture, and management decisions. It is the same machinery NASA uses after serious flight incidents. So the agency did not treat this as a plumbing problem. It treated it as a systemic failure worth months of investigation, and the findings describe a chain rather than a single mistake. Software that did not catch what it should have caught, procedures that did not adequately cover the operation being performed, a hydraulic backstop that had gone unverified for 21 years, and people working faster than careful practice would normally allow. There is a reason that finding about culture matters more than the hardware. Equipment failures can be engineered against with better parts and tighter tolerances. Procedural failures can be addressed by rewriting the procedures themselves. Both of those are solvable problems with reasonably known solutions. A culture that pressures operators to move quickly is different. It does not originate at the console where the mistake happens. It originates further upstream, in schedules that promise more than the network holds. The operator working as expeditiously as possible is responding rationally to that pressure. Which means the correction cannot happen only at Goldstone itself. It has to happen wherever the demand curve is being set, and that demand curve is heading toward a 10-fold increase. Remove any one link from that chain and the antenna probably survives. Every one of those links has to fail at once. On the 16th of September 2025, all of them did. The asbestos detail deserves a moment of attention as well. Structures built in that era commonly used asbestos in insulation and fireproofing. That material is safe while it stays sealed and undisturbed. Flood it with contaminated water and the situation changes completely. Now you have a hazardous material problem sitting inside your repair site. Abatement crews have to finish before engineering crews can even start. Add the upgrades that were already scheduled for this antenna anyway. The return to service date lands at approximately October of 2028. Compare that outage to the last major one this network absorbed. Canberra's 70-metre dish went down in March of 2020. That planned work took 11 full months to fully complete. That outage was planned years in advance and scheduled deliberately. Missions adjusted their operations knowing exactly when it would happen. It was an upgrade, not an accident, and it finished roughly on time. The Goldstone outage is different in every one of those respects. It was not planned, and nobody could schedule around it. It began with a mishap rather than a maintenance decision. And this outage is not 11 months long at all. It runs to roughly 37 months from start to finish. 3 years is not a maintenance window in any meaningful sense. 3 years is long enough for missions to launch and arrive. It is long enough for an entire fire season cycle to repeat 3 times. Track the arithmetic with me for just a moment here. From September 2025 to October 2028 is 3 years. For 3 full years, this network operates with 2 of its 3 largest antennas. 2, where the entire design assumed 3 would always be standing. And on the 24th of July 2026, fire crossed one of those 2. That is the anomaly that does not fit the comfortable version of Friday. When NASA said support transitioned seamlessly to Goldstone, that statement was accurate. Missions were covered and nobody lost a spacecraft, and I am not alleging spin. But Goldstone absorbed Madrid's workload while missing its own largest dish. The backup was already degraded before anyone asked it to be the backup. There is a second consequence to that antenna being down. It has nothing to do with talking to spacecraft at all. It concerns what we can and cannot measure about the rocks near Earth. I will come to that, and it changes how you read asteroid headlines. First, you need to understand why a 70 metadish matters so much. Because the signals these antennas chase sit at the absolute edge of physics. Part 5. The whisper that arrives weaker than anything you have ever measured. Voyager 1 is currently more than 38 billion kilometers from Earth. In miles, that comes to roughly 23.6 billion. It is the most distant object human beings have ever built. Light itself needs about 22.5 hours to cross that gap. So every command sent to Voyager 1 arrives a full day late. Every answer takes another day to come back to Spain or California. A single question and its reply is close to a 2-day conversation. The transmitter aboard Voyager 1 puts out about 22.4 watts. That is less power than the bulb inside a household refrigerator. It is less than the charger for your phone drawers overnight, and that signal must cross 38 billion kilometers of empty space. Here is where the physics turns genuinely brutal on this mission. Radio energy leaving an antenna does not travel as a beam of fixed width. It spreads outward, expanding as a widening cone across the distance. The area that energy covers grows with the square of the distance travelled. Double the distance, and the same energy smears across 4 times the area. Triple it, and you are down to 1/9 of the original strength. Picture blowing a soap bubble slowly and watching the film stretch. The soap gets thinner as the bubble grows because the same soap covers more surface. Voyager's signal is that film of soap on that expanding bubble. It has been thinning continuously for 48 years now. By the time that whisper reaches Earth, the arriving power is under 1 attowatt. An attowatt is 10 to the negative 18 watts of power. The National Radio Astronomy Observatory describes it as a billionth of a watt. I want to make that physical, because scientific notation hides how absurd it is. A digital wristwatch runs on roughly 1 microwatt of electrical power. A microwatt is 1/1,000,000th of a single watt of power. The signal arriving from Voyager 1 is about 1 trillion times weaker than that. Gather every photon of Voyager's signal falling on a 70-meter dish. Accumulate that energy across the entire lifetime of the mission so far. You would still not have enough to lift a single grain of sand. That is what these antennas hear, routinely, on an ordinary working day. So how is that even possible in the first place? 4 things make it possible, and each one is a place where failure lives. The first is aperture, meaning the raw collecting area of the dish. A larger reflector intercepts more of that thinning soap film. This is exactly why the 70-meter antennas matter so disproportionately. Collecting area scales with the square of the diameter, not with diameter itself. Doubling the width of a dish roughly quadruples the signal it captures. The second is surface accuracy, and this one becomes important later. A parabolic dish works by reflecting incoming waves to a single focal point. For that to work, the surface must hold its shape very precisely. It must stay accurate to a small fraction of the wavelength being received. At X band, near 8 GHz, the wavelength is about 3.7 centimeters. So a 70-meter structure must hold its shape within a few millimeters. It must do that in heat, in wind, and at every pointing angle. Thermal distortion is not a footnote anywhere in this system. It is a direct and measurable loss of usable signal strength. Carry that fact forward, because it decides what Friday actually cost. A dish can look perfectly intact and still have lost its precision. The third factor is noise generated inside the receiver itself. Every electronic amplifier produces its own electrical noise as it operates. If that internal noise is louder than the signal is unrecoverable. The network solves this by cooling its front-end amplifiers cryogenically. Temperatures drop toward a few degrees above absolute zero inside those packages. At that temperature, the thermal jitter inside the electronics falls dramatically. Only then can a signal weaker than an attowatt be pulled out. Which means the antenna itself is not really the instrument here. The antenna is the collector, gathering what little energy arrives. The instrument is a package of supercooled electronics inside the structure, and it only works while its cryogenic plant keeps running properly. The fourth factor is patience, which sounds soft but is not. You cannot push much data through a channel this week, so you send it slowly and wrap it in heavy error correction coding. Voyager's engineering data comes home at about 160 bits per second. A single photograph from your phone would take years at that rate. There is one more constraint I have not mentioned yet. Everything above assumes the antenna can actually see the spacecraft, but the atmosphere itself absorbs signal, and it absorbs more at low angles. When a spacecraft sits near the horizon, its signal crosses far more air. Water vapor in that air absorbs energy, particularly at higher frequencies, which is why these sites were placed in dry regions deliberately. The Mojave, the hills west of Madrid, and the Australian interior share that quality. Low humidity means less absorption and a cleaner signal path. It also means these complexes sit in landscapes that burn. Dry air is good for radio and dangerous for everything growing nearby. The property that makes a site good for listening makes it flammable. That trade was made in 1964 without anyone noting it. Now combine those 4 facts, and the 6-antenna array finally makes sense. Arraying means pointing several separate dishes at one spacecraft simultaneously. Their outputs are then combined, correcting for tiny differences in arrival time. Done correctly, the combination behaves like one far larger antenna. The working rule inside the network is straightforward and useful. 4 of the 34-meter beam waveguide antennas arrayed together. Approximate 170-meter dish. A similar trick exists on the transmitting side of the operation. Fitting a 34-meter antenna with an 80-kilowatt transmitter changes its reach. It then radiates roughly what a 70-meter dish does with 20 kilowatts. Hold 2 things in your head at once for a moment here. So a complex with 6 antennas rather than 4 is not merely convenient, it is more sensitive than anything else on the planet. 6 dishes can be combined into a listening device no single structure matches. Now here is the sentence from NASA and the Jet Propulsion Laboratory that matters most. A 5-antenna array is currently needed to downlink science data from Voyager 1. That data comes from its plasma wave system instrument out in interstellar space, and as Voyager gets further away, 6 antennas will be needed. 5 antennas are needed now, and 6 will be needed soon. Let that requirement sit for a second before we continue. Madrid is the only complex on Earth that currently has 6. Which raises an obvious question with a much less obvious answer. Why does this network have only 3 sites in the first place? Part 6. Why the number of these on Earth is exactly 3. The Deep Space Network rests on one geometric fact about our planet. The Earth rotates completely once every 24 hours or so. A spacecraft in deep space is, from our viewpoint, nearly fixed against the stars. It moves very slowly across the sky over months and years. So an antenna in California can see that spacecraft for part of the day. Then the planet turns, and the spacecraft drops below the local horizon. California is now pointing at solid ground rather than open sky. If you want continuous contact, you need another antenna elsewhere. That antenna must have the spacecraft in view when the first one loses it. Then you need a third for the gap after that one. Place 3 complexes roughly 120 degrees apart in longitude. The coverage closes into an unbroken circle around the planet. As one site rotates out of view, the next rotates in. There is always at least one dish with a line of sight. That is why these sites sit exactly where they sit today. Goldstone occupies a stretch of the Mojave Desert in Southern California. Madrid occupies the dry hills lying west of the Spanish capital. Canberra occupies a quiet valley at Tidbinbia in southeastern Australia. Each location was chosen for dry weather since atmospheric water absorbs signal. Each was chosen for surrounding hills that block terrestrial radio noise. Each sits in a country capable of hosting a partnership lasting decades. But the fundamental constraint driving all of it was longitude. 120 degrees, 3 sites, and that is the minimum. 3 is not a design preference somebody chose for elegance. 3 is the smallest number that closes the circle at all. You might reasonably ask why nobody simply builds a 4th complex. The answer involves several constraints that all point the same direction. First, the longitude has to be right, or the site adds nothing. A 4th complex placed poorly duplicates coverage that already exists. It would need to sit in a gap. And the gaps are ocean. The Pacific is enormous, and building there is not straightforward. Second, the site must be radio quiet across the relevant frequencies. That means distance from cities, from airports, and from major transmitters. Those requirements have become far harder to satisfy since 1964. Mobile networks, satellite constellations, and radar systems now blanket most inhabited land. Third, the host country must be a stable partner across decades. This is not a 5-year lease on a warehouse. Madrid has operated continuously through 60 years of political change. That kind of continuity is the actual product being purchased. Fourth, the construction timeline is measured in years, not months. A single new 34-metre antenna takes years from approval to service. A complete new complex would take considerably longer than that. The modernisation programme already running is 5 years behind its schedule. There is a partial workaround that deserves a mention here. Agencies do share tracking capacity with each other when necessary. The European Space Agency operates its own deep space stations. Those stations sit in Spain, in Argentina, and in Australia. Japan operates a deep space antenna of its own as well. Cross-support agreements let those networks back each other up occasionally. That capacity is real, and it has been used many times. But it is limited, because those networks are also busy, and most of those antennas are 35 metres or smaller, which means cross-support helps with routine passes and ordinary missions. It does not replace a 70-metre dish for the hardest links. Nothing on Earth replaces a 70-metre dish except another one. There is also a straightforward budget reality behind all of this. Ground infrastructure is not what excites anyone in a funding debate. Missions get named, launched and photographed, and they generate public attention. Antennas sit in deserts and valleys doing unglamorous work for decades, which means ground systems are a reliable place to find savings. When a program runs over budget, the pressure lands somewhere. It rarely lands on the spacecraft already built and waiting to launch. So the practical answer is that a 4th site is not coming. Whatever happens over the next decade happens with these 3, and that bare minimum is precisely where the problem begins. Think of this network as a 3-legged stool holding up a heavy load. That is not a metaphor for weakness, it is a description of the geometry. 3 legs, evenly spaced, and 3 is the fewest that stands. Remove one leg from a 3-legged stool and it does not wobble. It falls, because there was never a spare leg in the design. Keep that stool in mind, because we return to it later. The network does have redundancy, but not in the way most people imagine. Redundancy lives in the overlap windows, when 2 complexes see the same target. Outside those windows, each site is the only option for its slice of sky. There is a subtlety in how coverage actually works that is worth understanding. The handover between complexes is not instant or fully automatic. As a spacecraft sets at one site, it rises at the next. For a period, the 2 sites can both see it. That overlap is where handovers happen, and where redundancy genuinely exists. But the overlap window is not the same for every spacecraft. It depends entirely on the target's position in the sky. A spacecraft low on the horizon has a shorter mutual visibility window. Signals passing through more atmosphere also suffer more distortion and loss, so the practical redundancy varies from mission to mission and hour to hour. Which means the network does not simply lose 1/3 of capacity when a site goes down. It loses specific windows for specific spacecraft at specific times. Some missions barely notice, and others lose their only good pass. Now consider the sheer load riding on those 3 legs. Let me put a number on that load before we go on. The Deep Space Network supports communications for more than 40 active missions. Those missions are flown by close to 30 different countries around the world. That is not 40 spacecraft politely taking turns on a quiet schedule. Mars orbiters need daily relay passes to serve the vehicles below them. Rovers generate data volumes that must come down before the next working day. Juno needs its window at Jupiter, and Psyche needs navigation during cruise. New Horizons still reports back from beyond the Kuiper Belt. Europa Clipper is in transit and requires regular navigation tracking. Lunar landers keep multiplying as commercial missions reach the moon. Ask yourself what that scheduling meeting looks like every single week. Every one of those missions files a request for antenna time. Those requests flow into a scheduling process at the network's operations center, and that scheduling process is exactly where the strain becomes visible. The requests coming in exceed the hours physically available to grant. I am going to give you the precise figure shortly. It does not come from a critic outside the agency. It comes from NASA's own auditors, published in a public document, and almost nobody read it at all when it came out. Part 7. The 40% that was published and then ignored. On the 12th of July, 2023, a report was published. NASA's Office of Inspector General had audited the Deep Space Network. The document carries the reference number IG23-016. Anyone can download and read it right now without any special access. Understand what this document actually is before we go into it. This is not an outside pressure group complaining about the space agency. This is NASA's own internal watchdog examining NASA's own infrastructure. It published its findings under NASA's own letterhead for the public. Here is the central finding, phrased the way the auditors phrased it. The network is oversubscribed, meaning missions request more time than capacity can provide. Demand exceeds supply at times by as much as 40%. Hold that number, because a second one is coming behind it. The gap between the two is where this entire story lives. Let me translate 40% oversubscription into something you can picture. The scheduling office assembles a calendar of available antenna hours. The requests arriving from missions exceed those hours by nearly half again. Every one of those requests came from a real mission with real objectives. Behind each one sits a team that needs its data to work, so somebody has to say no to a substantial fraction of them. Passes get shortened, and observations get deferred to a later window. Science that was funded, built, launched, and flown across the solar system waits. That is the normal state of this network on an ordinary day. Not during a crisis, and not during a fire, but every week. Now here is the second number that I promised you earlier. The auditors projected that excess demand would reach 50% by the 2030s. They also noted something considerably starker about the near future. By early 2030, demand for network support is expected to increase tenfold. That means a factor of 10, not 10% more. 10 times the current demand landing on the same 3 sites. The reasons behind that projection are not mysterious at all. Artemis is returning crewed vehicles to the space around the moon. Crewed missions cannot tolerate the scheduling flexibility a robotic orbiter accepts. Europa Clipper is travelling toward Jupiter and needs tracking throughout. Psyche is heading for a metal asteroid nobody has visited. Dragonfly is coming soon, and commercial lunar landers keep on multiplying. Roughly 30 national agencies now contract with NASA for tracking support. There is a further wrinkle in how that oversubscription actually bites. Not all antenna hours are interchangeable with each other at all. A mission needing K-band cannot use an antenna without K-band. A mission at a southern declination cannot use a northern site. A spacecraft needing a high-power uplink cannot use a small dish. So the shortage is not a simple shortage of hours. It is a shortage of the right hours on the right antennas, which means the effective oversubscription for some missions is far worse than 40%. For a mission that can only use one specific antenna, availability is binary. Either that one dish is free, or the mission simply waits. Voyager 2 is the extreme example of that constraint, as we will see. But it is not the only mission with narrow requirements. Every spacecraft carries some combination of frequency, power, and geometry limits. Meanwhile, what exactly is all of that traffic queuing up for? The auditors were blunt about the state of the hardware. They described infrastructure, some of which was built in the 1960s. They characterized that infrastructure as carrying extensive and unfunded deferred maintenance. Do not skip past this next detail, because everything later depends on it. Madrid's first antenna went operational in 1965, as we established earlier. Deep Space Station 63 was built in the early 1970s. It was rebuilt once, in 1987, and has run since. Deferred maintenance sounds like a bureaucratic phrase, so let me strip that away. Deferred maintenance means work engineers identified as necessary, and nobody funded. It does not disappear because it went unfunded that year. It simply accumulates across decades of consistently tight annual budgets. And it is precisely the category into which one particular item falls. A hydraulic limit safeguard that had not been tested since 2004. So what exactly was being done about all of this problem? The answer is a program called the Deep Space Network Aperture Enhancement Project. It began in 2010 with a sensible and straightforward plan. Rather than build more 70-meter antennas which cost enormous sums, build smaller ones. Place 4 34-meter beam waveguide antennas at each of the 3 complexes. 4 of those arrayed together approximate one 70-meter dish. They are individually cheaper, more flexible, and far easier to maintain. If one goes offline for servicing, 3 others remain available. That is a good plan, and it is genuinely the right plan. Here is how the plan was progressing according to that same audit. At the start of fiscal year 2023, it was nearly 5 years behind schedule. Its costs had risen by 68% to $706 million. The program was 5 years late and 68% over budget. Physics Today covered the same findings under a 2-word headline. That particular headline called the network overburdened and badly underfunded. Now connect that audit directly back to Friday afternoon in Spain. Madrid was the first of the 3 complexes to finish its modernization. Deep Space Station 53 came online there in February of 2022. That completion is exactly why Madrid has 6 antennas today. Goldstone and Canberra still have 4 apiece because their builds came later. Madrid is not the largest complex by accident or by favoritism. Madrid is the largest complex because it received its upgrades first, which means the fire on the 24th of July crossed specific ground. It crossed the most modernized and highest capacity node in the entire network. It crossed the only site holding arraying capability the others cannot match. It crossed the single site whose loss would hurt the most, and it did so while Goldstone was already missing its largest antenna. In a year when NASA has been supporting Artemis II communications. With demand climbing toward a 10-fold increase across the coming decade, I want to give these engineers their due before going further. The network performed on Friday, and it performed under real pressure. NASA reported that it supported Artemis II communications in April of 2026. It did that while Deep Space Station 14 was entirely out of service. But there is an important difference worth stating carefully here. A robust system has spare capacity built into its design. A system staffed by people extremely good at absorbing failures is different. The first one has margin, and the second one has heroics. The auditors saw clearly where that difference eventually leads everyone. They wrote it down 3 years before any fire reached Robledo de Chavela. And to understand what was actually riding on Friday, you need the queue itself. Part 8. What 40 missions are actually queuing for. 40 missions is a number, and numbers slide off without something concrete. So let me make that queue physical for a moment. I want to be careful about one particular thing first. I do not have the Madrid tracking schedule for Friday afternoon. I am not going to invent one to make a stronger story. What I can describe is the class of work that Complex normally carries. That much of it is a matter of public record. Start with the Mars fleet, because it is the busiest customer. Multiple orbiters operate around Mars simultaneously, and several serve double duty. They act as relay stations for the vehicles working on the surface. A rover does not send its bulk data directly back to Earth. It sends that data to an orbiter passing overhead on a schedule. The orbiter then sends it onward to a ground station here. Break that ground link and the data does not vanish into nothing. It queues aboard the orbiter, and the queue has a finite size. More importantly, the next day's activity plan cannot go up. The rover cannot receive instructions until the previous results come down. A missed pass does not destroy science, but it slows the loop. Then there is Juno, on its long elliptical orbit around Jupiter. Its science happens in concentrated bursts around each close approach. The rest of that orbit is spent transmitting what was collected. Miss the transmission window, and you are waiting for the next orbit entirely. Ask yourself what that queue looks like during a genuinely bad week. Then there are the spacecraft in transit, like Psyche and Europa Clipper. Cruise phases look undemanding from outside, but they are not. They include trajectory correction manoeuvres executed at carefully chosen moments. A trajectory correction requires extremely precise navigation work done beforehand, and that navigation is performed using the radio signal itself. This next point surprises almost everybody who hears it stated. These antennas do not merely carry data back and forth. They are the navigation system for the entire deep space fleet. The network measures the round-trip time of a signal precisely. It measures the Doppler shift of that signal to extraordinary accuracy. That accuracy reaches fractions of a millimeter per second of velocity. When a spacecraft arrives within kilometers of its aim point, understand where that accuracy came from. It came from ground stations measuring a radio signal for months. No ground station available means no navigation solution at all. The dish is not simply a telephone line strung across space. The dish is also the ruler measuring where everything actually is. The volume of data involved has grown enormously over the decades. Early missions returned measurements that would fit on a modern text file. A single Mars orbiter now returns more data in a day than entire early programs did. High-resolution cameras and spectrometers generate far more than the link can carry, which creates a permanent bottleneck that has nothing to do with the spacecraft. The instruments can collect more than the network can bring home. Mission teams routinely decide what not to transmit because there is no capacity. That decision is invisible in every press release you will ever read. So when antenna hours are lost, science is lost with them. Not dramatically, and not in a way anyone announces publicly. It simply never gets collected, or never gets sent, or gets overwritten. There is also cross-support, which explains something about Friday. The Deep Space Network tracks spacecraft belonging to other agencies regularly. Other agencies track NASA spacecraft in return whenever it is needed, which is exactly why the European Space Agency station at Cerberus matters. Cerberus sits in Villa Province, roughly 77 kilometers from Madrid, it hosts a 35-meter antenna in the European tracking network. That station was also evacuated on the very same afternoon. The European Space Agency issued a statement about it the next day. It said that based on information currently available, the station appeared unharmed. Then, it said something remarkably honest for any agency to publish. It stated that it did not have physical access to the station. It could not therefore conduct any on-site inspection at all. That is an agency telling you plainly that it did not know. The agency believed that the station was very probably fine. It could not confirm that belief, because it could not get there. The agency also expressed solidarity with NASA in the same statement. It noted that the Madrid complex appeared to have been more directly affected, so 2 deep space ground stations on the same peninsula went dark together. 2 different space agencies, 2 evacuations, 2 sites believed intact and neither verified. There is one more thing worth knowing about how this queue works. NASA publishes a live display of network activity to the public. It shows which antennas are tracking which spacecraft at any moment. You can watch Madrid, Goldstone and Canberra working in real time. You can see which dish is talking to which probe right now. That display is unusually honest for a piece of public outreach. It shows the network as it actually is, minute by minute, and it means anyone can verify whether a complex is operating. During the days after the fire, that display told its own story. Madrid's antennas were not carrying anything like their usual traffic. Now, spacecraft are built to survive this kind of gap. Every one of them stores data aboard and tolerates missed contacts. Engineers plan for outages, and nothing I have described is a crisis alone. But one category of event does not wait for a free dish. An orbit insertion burn happens when the spacecraft arrives, not when convenient. A landing sequence executes on its own timeline regardless of scheduling. A trajectory correction has a window measured in hours, not days. For those events, the network simply clears the calendar entirely. There is no second attempt available if the window closes, which means the real cost of a strained network is usually invisible. It is not a lost spacecraft making headlines around the world. It is a continuous tax paid in shortened passes and deferred science. That tax buys certainty for the handful of moments that cannot move. That is what 40% oversubscription feels like from inside a mission team. All of which assumes the antennas themselves survive whatever arrives. On Friday, those antennas appear to have survived the fire front. There is one case in the record where they did not. That destruction took roughly 30 minutes from beginning to end. Part 9. 30 minutes at Mount Stromlo. I want to take you to Australia on the 18th of January, 2003. This next case is the one everybody in the field remembers. Mount Stromlo Observatory sat on a hilltop just outside Canberra. It belonged to the Australian National University and had operated since 1924. It was among the most important astronomical facilities in the Southern Hemisphere. Generations of Australian astronomers were trained on that particular hill. It sits roughly 10 kilometres from the Canberra Deep Space Communication Complex. That distance of 10 kilometres is going to matter very shortly. That summer, fires had burned in the mountains west of Canberra for days. Lightning had started them in early January across country deep in drought. Most people in the city treated them as a distant and manageable problem. Fires in the ranges were normal and expected every few years. Fires reaching the suburbs of a national capital were not. Pay close attention to the date attached to this particular one. On the 18th of January, the conditions aligned the way they occasionally do. Extreme heat arrived together with very low humidity and strong wind. The separate fires in the ranges merged into a single advancing front. That front ran east toward the city and built into something else entirely. Firestorm, and the word is technical rather than dramatic. A firestorm generates its own weather system as it burns. It produces winds that carry burning material kilometers ahead of the main front. The fire stops advancing along a line you can defend. Instead, it begins landing in front of itself, repeatedly, without warning. At the observatory, the evacuation order came at around 2:30 in the afternoon. The firestorm engulfed that entire site roughly 30 minutes later. I want that timescale to land properly before we continue. 30 minutes from the decision to leave to the destruction of an 80-year-old observatory. Not 30 hours of crews fighting a holding action through the night. The whole thing took half an hour from warning to ruin. 5 separate telescopes were destroyed on that hilltop in Canberra. Among them was the Great Melbourne Telescope, an instrument built in 1868. It had been in use for more than a century by then. It had been rebuilt and repurposed to survey the sky for dark matter. By evening it was gone entirely, and it was not alone. The 74-inch telescope, the observatory's largest optical instrument, was gone. The 50-inch telescope used for a landmark dark matter survey was gone. The workshops burned along with everything that was stored inside them. One of those workshops held an instrument called the Near-Infrared Integral Field Spectrograph. It was nearly finished and destined for the Gemini North Telescope in Hawaii. Years of work by a specialist team, weeks from shipping, reduced to slag. The broader fire that day killed 4 people across the region. It destroyed 488 structures in and around Canberra. Total damage was estimated at roughly 300 million Australian dollars. The observatory damage alone was first assessed between $12 and $20 million. Later assessments of the full university infrastructure loss exceeded 80 million. There is one more detail from that day worth carrying forward. The observatory had a bushfire plan, and the plan was followed. Staff evacuated promptly when they were finally told to evacuate. Nobody at Mount Stromlo died on the 18th of January. The plan worked exactly as intended for the people involved. It could do nothing at all for the instruments themselves. You cannot evacuate a 74-inch telescope in 30 minutes. You cannot carry a spectrograph out of a burning workshop. The hardware stays where it is and takes whatever arrives. That asymmetry matters enormously for what happened later in Spain. 90 people walked off that hillside, and every one of them survived. 6 antennas weighing millions of kilograms stayed exactly where they were built. Whatever the fire did to them, it did, while nobody was watching. Now here is why that fire belongs in this story. It is not because of the drama of the flames. Mount Stromlo was not a poorly protected or neglected facility. It was a major national scientific institution on a hilltop. It had cleared ground around it and established emergency procedures. It sat in a country with some of the most experienced fire agencies anywhere. It stood 10 kilometers from a deep space tracking station. It was in a city with professional emergency services on standby. And it burned to the ground in half an hour. Mount Stromlo was eventually rebuilt, but not as it had been. The site now hosts an advanced instrumentation centre rather than the old telescopes. Australian astronomers moved much of their optical work to Siding Spring instead. That observatory sits further inland, in the mountains of New South Wales. Siding Spring was itself threatened by fire in January of 2013. Flames reached the site and damaged several buildings on the mountain. The main telescopes survived that fire, unlike their counterparts a decade earlier. Staff there had watched Mount Stromlo burn and had planned accordingly, so the lesson was learned once, expensively, and applied elsewhere. The question worth asking is whether it was learned everywhere it needed to be. Everyone who works at a hilltop observatory in dry country knows this story. Mount Stromlo is the reference case for facilities of this type. It appears in risk assessments for observatories all over the world, so consider what Spanish officials said on Friday with that history in mind. Carlos Novillo said the fire was beyond the capacity of firefighters to contain. Francisco Martin described the situation at the complex as critical. Local officials said the impossible was being done to safeguard it. Those were not officials performing anxiety for the assembled cameras. Those were officials who understand what fire does to hilltop scientific installations. They know what happens when a front arrives carrying its own wind. I should flag one limitation in what I can tell you here. I have not been able to confirm from available sources whether the Canberra complex itself was evacuated. That applies both to 2003 and to the Black Summer fires of 2019. I am not going to assert something I cannot properly support, but the geography itself is not in any dispute at all. A deep space tracking complex sits 10 kilometers from a hilltop where 5 telescopes died. Those telescopes died in 30 minutes on a January afternoon, and Madrid on this occasion received the far better outcome. The reported damage was pavement and surrounding vegetation only, nothing more. No significant structural damage was observed to the antennas or buildings, so you might reasonably conclude that this is a story about a bullet dodged. You might conclude the mitigation worked and everyone should feel reassured. I want to argue that this conclusion is precisely wrong, because the danger in this story is not that a facility might burn. The danger is what happens in the years after one does, and for that, we need to go to Puerto Rico. Part 10. The 900 tons that fell and were never replaced. On the 10th of August 2020, a cable slipped in Puerto Rico. It was an auxiliary cable at the famous Arecibo Observatory. It pulled free of its socket and fell into the dish below. The impact tore a gash roughly 30 meters long across the reflector surface. Arecibo was one of the most recognizable scientific instruments on Earth. A reflector 305 meters across sat inside a natural sinkhole. Above it hung a 900-ton instrument platform on suspended cables. Those cables ran from 3 towers built around the rim. The observatory had been operating continuously since 1963. Engineers examined the failed socket and found something that changed everything. The cable had not been overloaded beyond its rated strength. It had pulled free through slow degradation in the zinc anchoring its strands. That process is sometimes described as zinc creep in the engineering literature. Combined with structural stress absorbed during Hurricane Maria in 2017, the implication was clear. The remaining cables could not be assumed sound simply because they still held. Repairs were planned anyway, and replacement cables were ordered immediately. Then, on the 6th of November, 2020, a main cable failed. Count the months with me, because the sequence matters more than anything. That failure was decisive in a way the first one was not. The platform now hung on a reduced set of cables of unknown condition. Engineers could not safely climb the towers to inspect what remained. On the 19th of November, the National Science Foundation announced decommissioning. There was no way to repair it without putting people underneath it. 900 tons hung above them and might come down at any moment. It came down before anyone could do anything at all. At roughly 8 in the morning on the 1st of December, the remaining cables failed. The platform swung once and then dropped into the dish below. The 3 towers snapped apart under the suddenly released load. An observatory that had run for 57 years ceased to exist in seconds. Arecibo did far more than one kind of science across those decades. Its shape made it extraordinarily sensitive despite being fixed in place. It could not steer like a conventional dish on a mount. Instead, it used a movable platform above a fixed reflector surface. That gave it access to a strip of sky overhead. Within that strip, it was unmatched for sensitivity for many years. It studied pulsars, and it mapped the ionosphere above Puerto Rico. It searched for signals from other civilizations across decades of observation. It measured the rotation of Mercury and corrected what astronomers believed. and it tracked asteroids with a precision nothing else could match. The collapse was captured on video from 2 separate angles. A drone happened to be inspecting the cables at that exact moment. Its footage shows the cable strands failing in sequence at the tower top. A second camera recorded the platform falling into the dish from a distance. That footage is unusual in the history of scientific infrastructure. Facilities are usually lost quietly, or after everyone has stopped watching. Arecibo's final seconds were recorded in high definition from the air. Engineers now study those frames to understand exactly how the failure progressed. There is something worth noticing carefully in that particular detail. The observatory was being watched constantly in its final weeks. Everyone understood the danger, and everyone knew it might come down. And still nothing at all could be done to save it. The decision not to rebuild was made on cost and risk grounds. The National Science Foundation faced enormous reconstruction expense with uncertain benefit. Other instruments had emerged that covered parts of Arecibo's work, but nothing replaced its planetary radar because almost nothing ever had it. The site was eventually cleared of all the collapsed structure. What stands there now is an educational centre rather than an observatory. A 305-metre aperture simply left the world's inventory. Nobody replaced it, and the world adjusted to having less. Now, why does a radio observatory in the Caribbean belong here? Because of one specific thing Arecibo could do that almost nothing else could. Give me one more minute on this, because it pays off shortly. Arecibo was one of only 2 facilities on Earth capable of planetary radar, not radio astronomy, which means passively listening to what arrives. Radar means transmitting an enormous pulse at a solar system object. Then, it means catching and analysing the echo that returns. That distinction carries the whole story, so let me make it concrete. When a telescope observes an asteroid passively, it sees a moving point of light. From brightness and an assumed reflectivity, you can estimate a diameter. The word estimate is doing enormous work in that sentence. Guess wrong about how dark the surface is, and your estimate collapses. Your size figure can be off by a factor of 2 either way, and impact energy scales roughly with the cube of the diameter. Radar does not estimate anything at all, because radar measures directly. The echo gives you distance to within meters of the true value. It gives velocity to within centimeters per second of truth. With enough returning signal, you can build an actual shape model. You discover it is actually 2 objects orbiting each other. You discover it tumbles end over end every 4 minutes. You refine the orbit until predictions extend decades instead of years. For any asteroid that comes close enough to reach, radar changes everything. It is the difference between a guess and a measurement. When Arecibo collapsed, NASA noted that Goldstone could continue characterizing near-Earth objects. That statement was completely accurate at the time it was made. The Goldstone Solar System radar is the only fully steerable high-power planetary radar anywhere. It typically transmits between 450 and 500 kilowatts. It works in X-band, near 8,560 megahertz. Across its operating life, it has characterized more than 160 asteroids. It has also studied comets, the Moon, and the inner planets. And the Goldstone Solar System radar transmits through Deep Space Station 14, the same antenna that over-rotated while tracking Juno last September, the same antenna that flooded itself with 200,000 gallons of contaminated water, the same antenna that will not return to service until October of 2028. Follow that sequence carefully, because it is the turn in this whole story. In 2020, humanity lost half its planetary radar capability at Arecibo. The reassurance offered at the time was that Goldstone remained available. In 2025, Goldstone's radar went offline for approximately 3 years, which means the capability that existed in 2019 does not exist now, and what that costs is measured in a unit almost nobody discusses. Part 11. What we stopped being able to measure about the rocks. I want to make that lost capability concrete, because it reaches all the way down. This is where a broken antenna in a California desert touches your life. Most near-Earth objects are discovered by survey telescopes scanning the sky. Those surveys look for points of light that move against fixed stars. They are excellent instruments, and they are getting better every year. But a survey gives you a position and a brightness, and nothing more. From brightness alone, you cannot separate a large dark rock from a small bright one. The standard practice is to assume an average surface reflectivity. You then convert the observed brightness into an estimated diameter. That estimate carries an uncertainty of roughly a factor of 2 either way. A factor of 2 in diameter is a factor of 8 in volume, which means roughly a factor of 8 in mass and in impact energy. Slow down here with me, because that arithmetic decides everything. When you read that an asteroid the size of a building passed close, consider the foundation. In most cases, that sentence rests on a brightness measurement and an assumption. The object might be half the stated size, or it might be double. Now let me give you the historical anchor that makes this real. On the 15th of February, 2013, an object entered the atmosphere over Russia. It exploded above Chelyabinsk at an altitude of roughly 30 kilometers. That airburst injured approximately 1,500 people across the region. Most of those injuries came from flying glass as windows blew inward. The energy released was estimated at around 30 times the Hiroshima bomb. The object itself was roughly 20 meters across, no larger than a house. 20 meters was enough to injure roughly 1,500 people. Nobody saw it coming, because it approached from the direction of the sun. No survey telescope on Earth can look into that glare, and 20 meters is small enough that even a nearby pass goes unremarked. Now go much further back for the second historical anchor. On the 30th of June, 1908, something exploded over Siberia. The event is known as the Tunguska airburst, above the Podkamennaya Tunguska River. It flattened an estimated 80 million trees across 2,000 square kilometers. Estimates of the object's size vary considerably, but most fall between 50 and 60 meters. Nobody died, because that region of Siberia held almost nobody. Hold those two numbers side by side for a moment. 20 meters injured 1,500 people in a modern city. Between 50 and 60 meters flattened 2,000 square kilometers of forest. The difference between those two outcomes is a factor of roughly 3 in diameter, and a factor of 2 in size uncertainty sits inside every brightness estimate. That is precisely the gap that radar exists to close. Radar ranging does something else that matters even more than sizing. It tightens an orbit so sharply that predictions extend for decades. A short observation arc gives you a few reliable years. Radar can turn that into confident forecasting across entire generations. That is how an object moves from being watched to being understood. Consider how many objects there are to characterize in the first place. Surveys are now finding near-Earth objects at a remarkable rate. Thousands of new discoveries are logged in a typical year. New survey telescopes coming online will increase that rate considerably, which creates a growing gap rather than a shrinking one. Discovery capability is rising quickly as new instruments reach full operation. Characterization capability fell when Arecibo collapsed and fell again last September. So the list of objects we know about grows every month. The list we can actually measure properly grows much more slowly. That gap is the practical consequence of losing planetary radar. It is not blindness, because the surveys still find things. Something more subtle instead, which is a catalogue full of estimates. So what exists right now, with Arecibo gone and Goldstone's dish in pieces? There are workarounds available, and skilled people use them very well. engineers can transmit using the 34-metre Deep Space Station 13. They then receive the returning echo at Green Bank in West Virginia. That two-site arrangement functions and it produces real science. But it delivers roughly 1/10 the sensitivity of Deep Space Station 14. There is also an S-band capability at Canberra on Deep Space Station 43. These are genuine tools operated by genuinely capable science teams. 1/10 the sensitivity carries a specific practical meaning though. You can only reach objects that come considerably closer to Earth, or objects that are considerably larger than the ones you are missing. The smaller and closer population becomes much harder to characterize. And that is exactly the population discovered days before it passes. There is a second reason radar matters that rarely gets discussed. Radar can detect whether an asteroid has a companion orbiting it. A surprising fraction of near-Earth objects turn out to be binary systems. Roughly 1 in 6 larger near-Earth asteroids has a moon. You cannot see that from a point of light in a survey image. That detail is not academic if anyone ever needs to deflect one. A deflection mission designed for a single body faces a different problem entirely when there are two. Mass, spin, and structure all change how an object responds to a push. Radar is how you learn those things before committing to a plan. Radar also tells you something about an object's internal structure. Many of these objects are not solid rock at all. They are loose collections of rubble held together weakly by gravity. Push one of those and it responds nothing like a boulder would. Lance Benner works at the Jet Propulsion Laboratory on radar observations. Benner has indicated a timeline for the antenna's return to radar work. Limited radar observations could become available as early as April of 2028. The system is expected operational some months before one particular event. That event is the close approach of asteroid Apophis in April of 2029. Read that schedule carefully, because it tells you two separate things. It tells you the people responsible understand exactly what is at stake. And it tells you the margin between repair and event is measured in months. I want to be completely clear about what I am not saying. I am not telling you an asteroid will strike Earth in the next 2 years. Nothing in current data supports that claim, and I will not imply it. What I am saying is narrower and, I think, more unsettling. For roughly 3 years, the sharpest instrument for sizing a passing rock is unavailable. The reason it is unavailable has nothing to do with asteroids at all. That antenna rotated past its stops while tracking a spacecraft at Jupiter. It then flooded itself with 200,000 gallons of contaminated water, and it did that because a safeguard nobody had tested in 21 years failed silently. That is the true cost of deferred maintenance, expressed in a useful unit. The unit that actually matters here is not dollars at all. The proper unit is resolution, and we have lost some. Which brings us to the spacecraft with the most to lose. That spacecraft has been flying for 48 straight years, and it now needs more antennas than any single site can provide. Part 12. The spacecraft that needs 5 dishes and will soon need 6. Voyager 1 launched on the 5th of September 1977. It has now passed beyond the heliopause into interstellar space. It returns the only direct measurements humanity has ever taken from that region. There is no second dataset anywhere, because no other spacecraft is there. New Horizons is travelling outward but remains decades from that boundary. It will also carry far less power when it eventually arrives. Voyager is powered by radioisotope thermoelectric generators aboard the spacecraft. Those convert the heat of decaying plutonium into usable electricity. That decay is relentless and cannot be altered by anyone. Available power drops by roughly 4 watts every single year. It has been dropping steadily for 48 consecutive years. I need you to hold the next sequence of dates in mind. The consequence is a slow amputation carried out one instrument at a time. Each Voyager launched carrying 10 separate scientific instruments on board. Each one is now operating with only 3 of them left. The recent sequence of shutdowns reads uncomfortably like a countdown. Voyager 2's plasma science instrument was switched off in October of 2024. Voyager 1's cosmic ray subsystem went off on the 25th of February. 2025. Voyager 2's low-energy charged particle instrument followed on the 24th of March. Voyager 1's equivalent instrument was shut down on the 17th of April, 2026. That last shutdown happened roughly 3 months before this fire. Suzanne Dodd manages the Voyager project at the Jet Propulsion Laboratory. Dodd explained the reasoning without any softening of it at all. She said that without turning off an instrument on each Voyager, the outcome was clear. The spacecraft would probably have only a few more months of power. After that, the team would need to declare end of mission. A few more months is the entire margin those engineers work inside. Every instrument switched off buys time for the ones still running. The hope is to keep at least one instrument alive into the 2030s. It is worth stating what those remaining instruments are actually measuring. Out beyond the heliopause, the spacecraft samples the interstellar medium directly. It measures magnetic field direction and strength in a place nothing else reaches. It counts charged particles arriving from across the wider galaxy. And the plasma wave instrument measures the density of the medium itself. That last measurement is the one requiring 5 arrayed antennas. The plasma wave data tells us how dense interstellar space actually is. Before Voyager crossed that boundary, those numbers were models and estimates. Now they are measurements, taken in place by a machine from 1977. When that link finally ends, the measurements end with it. There is no archive to consult and no second instrument to check. Whatever has not been transmitted by then simply never arrives. Now connect that spacecraft directly back to the ground in Spain. Because of the distance and the inverse square law we walked through earlier, something has changed. The signal from Voyager 1's plasma wave system can no longer reach a single antenna. Not a 34-metre dish, and not even a 70-metre dish. NASA and the Jet Propulsion Laboratory have stated the requirement plainly. A 5-antenna array is currently needed to downlink that science data. As Voyager gets further away, 6 antennas will be needed instead. Remember the soap bubble stretching thinner as it expands outward. That film is now so thin that 5 collectors barely catch it. Soon 5 will not be enough, and only one site has 6. On the 20th of April, 2024, Madrid pointed all 6 at Voyager 1. It was the first time that configuration had been attempted there, and here is a detail I want to present with real care. That same date carries a second piece of Voyager history. The 20th of April, 2024 is also when the spacecraft came back. Let me tell you that story, because it shows what these stations are for. On the 14th of November, 2023, Voyager 1 stopped making sense. The spacecraft was still transmitting, and the carrier signal was still arriving. But the data coming down was a repeating and unreadable pattern. The onboard flight data subsystem packages science and engineering data for transmission. It had failed in some way the team could not see. Think about the position that puts an engineering team into. Your patient is 22.5 hours away at light speed. You cannot look inside it, and you cannot simply restart it and hope. Every diagnostic command takes a day to arrive and a day to answer. You get one attempt at a time in sequence for months, and the spacecraft's remaining power is being counted in months as well. In March of 2024, the team sent a command informally called a poke. It asked the computer to dump its memory in a different way. The readout that came back finally revealed the underlying cause. A single memory chip had failed somewhere inside the subsystem. That chip held about 3% of the flight data subsystem's memory. Critically, part of what it held was software code the computer required. You cannot replace a failed chip at 15 billion miles from Earth. So the engineers did something considerably harder than that instead. They took the affected code and broke it into smaller sections. They found unused areas of memory scattered elsewhere in the system. They distributed those code sections around the dead chip entirely. Then they rewrote every cross-reference so each piece could find the others. Consider what that work actually required from those particular people. They wrote a patch for hardware designed in the early 1970s. Many of them learned that programming environment from archived documentation. They did it to route around a physical fault nobody could ever touch. Then, they transmitted it across the solar system and waited 2 days. The fix went up on the 18th of April, 2024. Linda Spilker is the Voyager project scientist, and she described the room. In the minutes before the signal was due, she said, "You could have heard a pin drop. On the 20th of April, the data came back readable. That is what a ground station actually is at the end of everything. Not a dish sitting on a hill in the sun, a room full of people who can hear an attowatt, and who can use that thread to repair a machine older than themselves." Voyager 2 carries its own version of this same dependency. Its version is even starker than the one you just heard. Part 13. The single antenna on Earth that can still reach Voyager 2. Voyager 2 flew past Neptune and its moon Triton in 1989. That encounter did something permanent to the spacecraft's onward path. The gravitational geometry of the flyby bent its trajectory steeply southward. Voyager 2 has been climbing below the plane of the planets ever since. From Earth, that spacecraft now sits low in the southern sky. It is permanently out of view from northern hemisphere antennas. Goldstone cannot see it, and Madrid cannot see it either. Only the southern complex at Canberra has a usable line of sight. But it is narrower than even that, and this is the part people miss. Not every antenna at Canberra is able to command Voyager 2. Only Deep Space Station 43 can do it, the 70-meter dish. That antenna carries the S-band uplink transmitter with sufficient power. It is tuned correctly for a spacecraft designed in the early 1970s. That is one antenna, not one complex, and not several options. One specific structure, in one valley, in one hemisphere of Earth. Notice how extraordinarily thin that particular thread has now become. Every instruction Voyager 2 has received since 1989 came through that dish. Every course adjustment, every instrument shut down, and every software change. If Deep Space Station 43 cannot transmit, nobody can talk to Voyager 2. Consider what commanding a spacecraft at that distance actually involves. You are not sending a message in any ordinary sense. You are transmitting a precisely timed sequence of radio pulses across billions of kilometers. Those pulses must arrive strong enough for a receiver designed in 1972. That receiver was built with the electronics available at that time. It cannot be upgraded, replaced, or repaired by anybody now. So the uplink transmitter on the ground has to do all the work. It compensates for a receiver that was never designed for this distance. That is why the requirement lands on one specific antenna. Only Deep Space Station 43 carries a transmitter powerful enough for the job. Smaller dishes at the same complex cannot substitute for it. There is a further constraint that makes this narrower still. The spacecraft is drifting further below the plane of the planets each year. Its position in the southern sky continues to sink slowly, which means the geometry does not improve at all over time. It only becomes more restrictive as the mission continues onward. It is worth remembering what Voyager 2 still does out there. It crossed into interstellar space in November of 2018. That crossing came 6 years after Voyager 1 made the same transition, and the two spacecraft crossed at different points and in different conditions. That difference turned out to be scientifically very valuable indeed. Having two probes cross the same boundary in two places revealed structure. The heliopause is not a smooth uniform shell around the solar system. It varies, and the only way anyone knows that is from two crossings. Both spacecraft are still returning data from beyond that boundary, and every bit of it arrives through ground stations on this planet. We already know what that looks like, because it happened. In March of 2020, that antenna went down for upgrades. The work lasted 11 full months from start to completion. For those 11 months, Voyager 2 could transmit to Earth normally, but it could not receive a single command from anybody. Think about the specific vulnerability that creates for a mission team. The spacecraft is still talking, so you know it is alive. You can watch its telemetry and see its systems reporting, and if something goes wrong, you can do absolutely nothing about it. You would simply watch it happen across a delay of many hours. NASA re-established contact with a test command later in 2020. That test command was the first the spacecraft had received in roughly 8 months. It worked, and the mission continued, and most people never heard about it. Jeff Berner is the chief engineer of the Deep Space Network. Berner commented on the situation while those repairs were underway. He said the 11 months of repairs obviously put more constraints on the other sites. Read that sentence with everything you now know behind it. That was the network absorbing a single planned outage at one complex. It was planned years in advance and scheduled very deliberately. Every mission knew it was coming and prepared for it accordingly. On Friday, the network absorbed an unplanned outage at a second complex. It did so while a third complex is missing its largest antenna, and that third complex will stay that way until October of 2028. There is one detail about Voyager 2 worth adding here. The spacecraft can still transmit, even when it cannot receive. That asymmetry exists because transmitting and receiving are different problems. Coming down, the signal only needs a large enough dish to catch it. Going up, the signal needs enough power to be heard aboard. The spacecraft's receiver is small, old, and cannot be improved. The ground transmitter has to overcome all of that from here, which is why the downlink works from several antennas and the uplink works from one. It is an unusual kind of dependency to build a mission on. Nobody designed it deliberately, and nobody could have avoided it. It emerged from a trajectory chosen at Neptune in 1989. Let me put the whole configuration in one place for you. 3 complexes hold humanity's entire connection to everything in deep space. One of them has a 70-meter dish flooded and offline for 3 years. One of them was evacuated on Friday with fire crossing its grounds, and one of them holds the only uplink to Voyager 2 in existence. Return for a moment to that 3-legged stool from earlier. One leg has been partly cut through since last September. On Friday, somebody lit a fire underneath the second leg. The third leg is carrying a mission nothing else on Earth can reach. The stool did not actually fall over on Friday afternoon. Engineers shifted the load across the network and it held. That is genuinely worth saying clearly and without any qualification. But a stool that holds under 2 damaged legs is not a stable stool. It is a stool that has not yet been asked the wrong question, and the load riding on it is scheduled to increase 10-fold. So what would it actually take to break one of those legs? Most people assume that they already know the answer here. Most people are wrong about it, and the reason is genuinely surprising. Part 14. The lie your eyes tell you about smoke. I want to correct something almost everyone assumed on Friday. I assumed it myself before I looked into the physics properly. The instinct is that smoke must be the operational problem. a sky filled with dense particulate matter above a receiving antenna, contact degraded or entirely lost while the plume sits overhead. Stay with me here, because this next point is genuinely counterintuitive. That instinct is completely wrong, and understanding why reveals the real danger. Smoke devastates optical astronomy in a way that is hard to overstate. A telescope working in visible or infrared light collects photons. Those photons have wavelengths measured in fractions of a micrometer. Smoke particles sit in a size range that scatters those wavelengths efficiently. They absorb them as well, across the whole visible spectrum. An observatory sitting under a smoke plume is effectively blinded. That is why fire season is an operational emergency for optical observatories worldwide. Radio operates inside a completely different physical regime from that. The Deep Space Network works at S-band near 2 GHz. It also works at X-band near 8 GHz across the network. It works at Ka-band as well, near 32 GHz. The wavelengths involved run from centimeters down to a few millimeters. Smoke particles are far too small and far too sparse to matter. Waves of that size pass through a plume essentially unaffected, so an antenna sitting beneath a smoke column keeps working normally. All else being equal, the signal arrives exactly as it should, which means the threat to these facilities was never the smoke. The threat is fire itself and everything that fails alongside it. Let me walk through the actual failure modes quite carefully. They are not the ones that most people would guess. Start with the reflector surface, and recall what we established earlier. A 70-meter dish must hold its parabolic shape within a few millimeters. It must do that across a span of 70 meters, at every angle. That surface is assembled from individual aluminium panels on an adjustable backing structure. Those panels are aligned during commissioning using precise survey equipment. The tolerances involved would be respectable on a precision machine tool. Heat distorts metal, and uneven heat distorts it very unevenly. A fire front produces intense radiant heat across one side of a structure. That introduces a thermal gradient the original design never anticipated. The resulting deformation does not need to be visible from the ground. A dish can look completely fine and still have lost efficiency. The only way to find out is to run a proper survey afterward. This is one reason a drive-through inspection cannot certify an antenna. It can tell you the antenna is standing on its mount. It cannot tell you whether the antenna still focuses correctly. Those are two entirely different statements about the same structure. Now go down into the pedestal, where these machines are genuinely vulnerable. Inside and beneath the dish sits everything that makes it an instrument. The azimuth bearing and drive systems rotate millions of kilograms on command. Hydraulic systems manage motion and hold position against wind loading. Elevation drives tilt the whole structure through its full range. Cable runs carry data and power throughout the entire mount. And critically, the cryogenic plant sits down there as well. So do the supercooled low-noise amplifiers we discussed earlier. Those are the components that make hearing an Atawatt possible at all. Remember the wristwatch, and how much weaker Voyager's signal is than that. The cryogenics are the part nobody outside the field thinks about. If the cooling system loses power, those amplifiers begin warming up. If its supply lines are compromised, the same thing happens. If its control electronics are damaged, the same thing happens again. A warm amplifier generates enough internal noise to bury any weak signal. The dish remains intact and the structure itself remains sound, and yet it can no longer hear Voyager at all. How do I know this class of damage is the real risk? Because it already happened to a 70-meter antenna last September. When Deep Space Station 14 over-rotated at Goldstone, the reflector did not fall. Nothing collapsed, and nothing was visibly destroyed from a distance. The damage that removed it from service for 3 years was elsewhere, It was fluid, cabling, and structural connections in and around the base. 11 fluid hoses require replacement before any other work proceeds. At least 85 of 114 data and power cables need replacing. All 56 structural connecting rods must come out and go back, and asbestos abatement in the flooded portions must happen first. That is the anatomy of how one of these machines actually dies. Not a dramatic collapse filmed from some nearby ridgeline. A pedestal full of ruined cable and contaminated fluid, and 3 years of work. And notice the detail one final time, because it is the sharpest here. The water that caused all of that came from the fire suppression system. The system installed to protect that antenna from exactly what arrived in Spain. There is one more way these antennas lose signal, and it comes from above. The sun interferes with deep space communication on a predictable schedule. Every 26 months or so, Mars passes behind the sun from our viewpoint. When that angle drops below roughly 3 degrees, signals cross the corona. Turbulent plasma there scatters and distorts everything passing through it. Carrier lock becomes unreliable, and the data arrives badly corrupted. The Jet Propulsion Laboratory responds by imposing a command moratorium. Teams deliberately stop sending instructions to Mars spacecraft for weeks at a time. A corrupted command is considerably worse than no command at all. Solar radio bursts create a related problem at the receiving end. They raise the noise floor inside the ground station itself. That reduces the margin between signal and noise on every link. So the sun does degrade this network on a known and repeating cycle. For context, solar cycle 25 reached its smoothed peak around October of 2024. It appears to have exited the solar maximum phase around February of 2026. So solar interference should trend downward across the next several years, which means the sky above these dishes is not the rising threat. The rising threat is standing on the ground all around them. Which means the honest question after Friday is not whether the dishes survived. The honest question is what nobody has been able to check yet. Part 15. What has to happen before anyone can call those dishes safe? Roughly 24 hours after the evacuation, NASA released its first assessment. It came through Press Secretary Bethany Stevens on the 25th of July. Stevens reported that an initial on-site inspection had been carried out. That inspection was performed by the Madrid Complex Emergency Response Team. It found wildfire damage primarily to pavement and surrounding vegetation. It observed no significant structural damage to antennas or to buildings. That is good news, and it is real, and I will not diminish it. But read the second half of what Stevens actually said. She added that the situation remained dynamic on the ground. She said comprehensive assessments would proceed as conditions stabilized and access improved. That is not a final engineering report on 6 antennas. That is a preliminary look conducted under active fire conditions. It was carried out by a team evacuated the previous afternoon, and the coverage that followed largely ignored the second sentence. There was disagreement in the reporting even about basic facts. The Spanish outlet Zetaca reported a NASA spokesman confirming the fire penetrated the grounds. The technology publication Wired reported that the impact on sensitive equipment remained unclear. Both of those statements can be entirely true at the same time. Fire crossing open ground is one particular kind of event. Fire damaging a cryogenically cooled receiver package is a completely different event. You cannot distinguish between them from a drive-through inspection. So what does a real assessment actually involve, and why does it take time? Start with the reflector surface on every single affected antenna. Verifying surface accuracy on a 70-meter dish is not visual work. It is a formal survey using highly specialized measurement techniques. Slow down on this, because it explains why nobody can rush the answer. Historically, that meant theodolites and photogrammetry across the reflector face. More recently, it involves laser scanning and a technique called radioholography. In holography, the antenna observes a source of known characteristics. The measurements are then processed into a map of the surface. That map shows which panels have moved and by exactly how much. If panels have shifted, each one is readjusted individually by hand. On a structure with hundreds of panels, that is days of work. Follow this one carefully, because it is where the reassurance runs out. Then comes the cabling, which is more insidious than people expect. Heat damage to cable insulation rarely produces an immediate obvious fault. It produces a degraded insulator that works perfectly well for a while. Then humidity arrives, or vibration, or one hot afternoon in August. What follows is an intermittent fault that takes weeks to trace. The only way to gain confidence is to test every run. On a structure with over 100 separate runs, that is slow. Then comes the cryogenic chain, and there is an elegant way to check it. You point the antenna at a radio source of known brightness. You then measure precisely what the receiving system reports back. That measurement gives you the system's actual working sensitivity today. You compare that figure against what the same antenna produced last month. If the number has moved, something in the chain has changed. That is true even when every visible component looks completely intact. There is a reason I keep returning to that Goldstone antenna. Then come the mechanical systems throughout the mount and pedestal. Drive motors, gearboxes, the azimuth bearing, the hydraulics, and the brakes. Limit switches, and every safety interlock built into the structure. And here the Goldstone investigation earns one last mention again. That board found a hydraulic limit safeguard untested since 2004. If a single lesson is available from that report, it is simple. On a structure this size, the components you assume are fine are dangerous. Those are precisely the components that end up in mishap board findings. Then comes site infrastructure that has nothing to do with radio. Power feeds into the complex and the backup generators behind them, the water supply serving the site and everything depending on it, and the fire suppression system itself, which now needs verification. Not verification that it exists, but verification that it functions. That a site that has just demonstrated fire can reach it, ahead of the 2 months when Spanish fire risk historically peaks. Here is where the reassuring version of Friday starts to thin out. Underneath every one of those checks, there are the people. These are not mainly NASA employees walking that Spanish hillside. Spain's National Institute of Aerospace Technology operates the Madrid complex. The engineers and technicians who evacuated on Friday are largely Spanish. Many of them live in the towns evacuated alongside the complex itself. Some have worked at that site for decades of their careers. They work on a facility whose lineage reaches back to Fresnadillas de la Oliva. That is a line running back to the first moon landing. I mention this because the coverage of Friday was almost entirely about hardware, 6 antennas at risk, and dishes that appear undamaged afterward. The hardware is genuinely what makes this matter at a planetary scale. But somebody had to decide in stages who left and when. Somebody configured equipment for an unattended shutdown with fire approaching. Somebody in California picked up traffic that had been Spanish an hour earlier. They folded it into a Goldstone calendar that was already full. They did that in real time while missing their own largest antenna. That is the actual redundancy in this system, when you look closely. It is not the geometry of 120 degrees. It is people who know how to use that geometry under pressure. And that is the part nobody can fund into existence quickly. You can appropriate money for a new antenna and wait a decade. You cannot appropriate an operations team carrying 30 years of institutional memory. There is one more question that always follows an event like this. It deserves a direct answer rather than an easy dismissal. The question is whether all of this represents some hidden pattern, whether facilities are failing in a coordinated way nobody will explain. Look at the base rates before reaching for that conclusion. Spain experiences many thousands of wildfires in a typical summer. In a bad year, hundreds of thousands of hectares burn there. The Madrid complex has stood in those hills for 60 fire seasons. This is the first time a front has crossed its grounds. That is not a facility being singled out by anything. That is a facility that was lucky for 6 decades. The equipment failures do not support any concealment theory either. The Goldstone board published findings that reflect badly on the agency. A cover-up does not look like a public report describing your own culture. Arecibo's collapse was traced to zinc creep and hurricane stress. The engineering forensics were published and contain no mystery at all. The oversubscription problem was documented by NASA's own Inspector General. So no, I do not see evidence of anything being hidden. What I see is worse in a way, because it is ordinary. These events share a common condition rather than a common cause. Each one is an aging, oversubscribed system meeting a completely normal stressor. Hurricanes hit Puerto Rico and antennas get operated under time pressure. And Spain burns every single summer, without any exception at all. None of those stresses is exotic or unpredictable in the slightest. They are producing outcomes now because the margin that absorbed them is gone. Which brings us to the 2 measurements that actually define the next 3 years. Part 16. 2 lines that cross inside the same 3 years. Everything so far belongs to one of 2 separate stories, and those 2 stories are now moving directly toward each other. Let me draw the first of those 2 lines clearly. The Madrid complex was sited in 1964 for good reasons. The engineers needed dry weather so atmospheric water would not absorb signal. They needed hills to shield the site from terrestrial radio interference. They needed the right longitude and a politically stable partner nation. They solved every one of those problems remarkably well indeed. Wildfire was not among the primary threat scenarios shaping that design. In the Sierra de Guadarrama of that era, fire was a manageable hazard. You handled it with cleared ground and a reliable water supply. Keep one eye on the calendar as I lay this out. Here is what changed underneath that original 1960s design. Western Europe recorded its warmest June on record in 2026. The Copernicus figure was 20.74 degrees Celsius. That sat 3.05 degrees above the recent baseline. It broke the record set in June of 2025. 2 consecutive record-breaking Junes, measured and published by the same service. The World Health Organization's European office added another useful measurement. It reported a 57% increase in wildfires across its European region. That increase is measured against the year 2022. And in the comparison that matters most here, Spain and Portugal each recorded a doubling. Both showed a 100% increase against the previous year. A doubling, year over year, in the country hosting this complex. For scale, 2022 was already the European Union's second worst season on record. More than 900,000 hectares burned across the Union that year. Spain accounted for somewhere around 310,000 of them. So the first line is fire risk in the Sierra de Guadarrama. It is not projected to rise at some future point. It is rising now, measured across consecutive record-breaking years. Now let me draw the second of those 2 lines. In September of 2025, Deep Space Station 14 went offline. It does not return until roughly October of 2028. In 2023, NASA's auditors documented 40% oversubscription. They projected 50% oversubscription arriving within the 2030s. They described infrastructure dating to the 1960s carrying deferred maintenance. they found a modernization program 5 years late and 68% over budget, and they projected demand rising tenfold by early 2030. So the second line is network margin, and it is falling. Now put both lines on the same chart and find the crossing. Fire risk climbs through a period of consecutive record heat. Network margin now sits at its lowest point in decades. That margin does not recover until Deep Space Station 14 returns. The overlap runs from roughly 2026 through 2028. That is 3 fire seasons stacked inside one repair window. We are currently inside the first of those 3 seasons, and I want to be precise about where inside it we sit. The fire that crossed Robledo de Chavela arrived in July. In Spain, the fire season does not peak in July. It peaks across August and September, historically and very consistently. That complex has been through the opening of the season. It has not yet been through the middle of it. Picture a balloon being inflated slowly by a steady pump. Somebody is simultaneously letting air out through a small pinhole. The escaping air is real, and you can hear it clearly. You could point at it and say pressure is being released. But if more air enters than escapes, the balloon still fills. The engineers are the pinhole in this particular physical arrangement. Every workaround and every schedule rearrangement releases some genuine pressure. The Voyager memory patch was exactly that kind of release. Those people are extraordinarily good and have absorbed this for years. The pump is demand, deferred maintenance, aging structures, and delayed modernization. And the pump is running considerably faster than the pinhole. Now let me handle the sky honestly, because it matters less than headlines suggest. On the day of the fire, the sun was moderately active. At approximately 4:24 Universal Time, a filament erupted in the southeast quadrant. It was associated with a C2.4 flare. It produced what forecasters classified as a partial halo coronal mass ejection. First analysis suggested a possible Earth-directed component arriving late on the 27th. There was a slight chance of G1 conditions, the lowest storm category. Minor solar activity had already occurred earlier that same week. G1 conditions were reached late on the 23rd of July. A warning issued the following morning extended elevated activity through midday. I could not confirm a formal storm watch for that arrival. Earlier that month there had been a genuinely significant episode. An X1.1 flare on the 30th of June produced a full halo ejection. That drove a G2 watch and storm conditions reaching G3. Those conditions occurred around the 3rd and 4th of July. That earlier event was real and properly forecast at the time. So let me state it plainly and without any inflation. The space weather that day was minor and did not cause the outage. If I claimed fire and solar storm converged to darken a station, that would be false. The available data simply does not support that particular story. For context, Solar Cycle 25 reached its smoothed peak around October of 2024. It appears to have exited the solar maximum phase around February of 2026, which means solar activity should trend downward rather than upward, which leaves the ground itself as the genuinely rising threat. The solar risk is cyclical, well characterized and currently declining. The fire risk is rising, measured across consecutive record years. And it arrives on a schedule set by August weather. So what happens next? And how exactly will anyone know? There are 2 branches, and the honest approach is describing both. In the first branch, the comprehensive assessment confirms the preliminary finding. Panel surveys come back with intolerance across every affected antenna. Cable runs test clean, and the cryogenic systems verify normally. The complex returns to full operations within days or a few weeks. Madrid resumes carrying its share, including the arraying Voyager depends on. Deep Space Station 23 comes online at Goldstone as planned. Deep Space Station 14 proceeds through repair and returns in late 2028. In the second branch, the detailed assessment finds what eyes could not. Thermal distortion in reflector panels requiring resurvey and realignment work. Damage to cable insulation appearing as intermittent faults over months. Compromised cryogenic or hydraulic components buried deep inside the pedestal. Fire suppression lines requiring full replacement before the season continues. Any of those removes an antenna from the schedule for weeks or months. And if it is the 70-meter dish, the network drops to 1. Or the much simpler version of escalation arrives here instead. Another front in August or September, when the season actually peaks. At a site whose vegetation buffer has already partly burned away, weigh both of those against each other before you decide anything. So which branch does the current available data actually support? The most honest answer available runs in two directions at once. The antennas are probably fine, and we should know within weeks. The season is probably not finished, and nobody knows when. Here are the indicators worth tracking, and every one is public. First, the comprehensive damage assessment from NASA and from Spain's Aerospace Institute. Second, the live display showing which antennas track which spacecraft. If the 70-meter dish stays quiet while smaller ones return, notice that. Third, watch for any 6 antenna arraying pass on Voyager 1. And fourth, the 2 milestone dates on Deep Space Station 14. Those 2 dates bound everything that we have covered here. April of 2028 for limited radar capability. October of 2028 for full return to service. If they slip, the window everyone is living inside gets longer. Part 17. The most dangerous Tuesday. 90 people walked out of a facility in the hills west of Madrid. A fire front officials had called uncontainable was moving toward their antennas. They got out safely, and the fire went through the grounds. The following day an inspection team went back in there. It found damage primarily to pavement and to surrounding vegetation. It observed no significant structural damage to the antennas or buildings. I do not want to leave a distorted impression of that outcome. Nobody died at Robledo de Chavela on the 24th of July. The dishes are standing and the missions kept flying without interruption. NASA moved the traffic to California and the network held together. The redundancy engineers built into this system in the 1960s worked. They built it for reasons that had nothing to do with wildfire. It worked anyway in 2026 for a threat nobody anticipated. That is a genuine engineering success, and those people deserve to hear it. But there is one thing I cannot stop turning over. The reason Friday worked is that somewhere existed to move the traffic. That is the entire mechanism holding all of this together. 3 sites, 120 degrees apart, covering for each other. And that mechanism has been quietly thinning for years now. One of the 3 has been missing its largest antenna since last September. The program meant to compensate is 5 years late and badly over budget. Demand is heading toward a 10-fold increase across the coming decade. NASA's own auditors wrote all of that down in 2023. What comes next on that hillside. Engineers will return with survey equipment and begin working through the antennas. They will measure surfaces, test cables, and verify cooling systems in sequence. That work will take days or weeks depending on what they find. Meanwhile, the fire season continues across central Spain into September. The vegetation that burned around the complex will not carry fire again soon. Everything beyond that burned margin is drier now than it was in July. And Deep Space Station 14 remains in pieces in the Mojave Desert. Crews there continue replacing hoses, cables, and structural rods on schedule. That antenna is not coming back before October of 2028, which means the thing that saved everyone on Friday is the thing being spent. There is one thing about Friday that will not appear in any report. For several hours, a group of Spanish engineers stood outside their own workplace. They watched a fire-front crossground they had maintained for years. They could not go back in, and they could not do anything. Everything those people are responsible for was inside that perimeter. 6 antennas, 60 years of operational history, and a link to interstellar space. All of it sat there while the front came through. That is the part of infrastructure that nobody ever photographs, not the dish against a blue sky, which is the image everyone uses, the people standing on a road watching with no remaining options. So the question stands where it stood at the beginning. Was the 24th of July a near miss, or was it a rehearsal? I do not think the available data lets anyone answer that yet. If the assessment comes back clean, and the new antenna arrives on time, one answer holds. If a front returns in September, or the surveys find what eyes missed, another does. Either way, the people who will know are currently walking a hillside in Spain. Their results will not appear on any evening news program. Hold one final image in your mind before we finish here. Everything genuinely at stake in this story is invisible to the eye. The signal is a billionth of a watt. The damage that matters is millimeters of distortion in a metal panel. The threat is a schedule slipping inside a document nobody downloads. And the prize is a 48-year-old spacecraft in interstellar space. It runs on 3 instruments and returns measurements nothing else can take. Its science data now requires 5 antennas working as one. Very soon that spacecraft will require 6 of them instead. There is exactly one place on Earth that has 6. On the 20th of April, 2024, those 6 pointed together at Voyager 1. On that same date, after 5 months of silence, Voyager spoke clearly again. Linda Spilker said, "You could have heard a pin drop in the room." 2 years and 3 months later, fire crossed the ground beneath those antennas. Watch what happens to public attention across the next few weeks. Nobody will fund a second 6 antenna complex because of one Friday. The assessment will finish and the results will be filed away. The network will go back to carrying 40 missions with too few hours. And the next fire season will arrive precisely on schedule. The most dangerous moment in a story like this is never the fire itself. It is the following Tuesday, when everyone decides it turned out fine. 90 people walked off that hill, and the dishes are still standing, and August has not happened yet on that Spanish hillside.